this lesson, we'll implement the Harry Markowitz mean variance framework with our programming. First, we'll recap the mean variance framework. Subsequently, we'll discuss the tail risk measures, namely value at risk, that is VAR, conditional value at risk, CVAR, and expected shortfall, ES. Next, we'll download securities data from Yahoo Finance. Then we'll compute returns and visualize various properties of this data. Next, we'll initiate a portfolio object, formulate various portfolio constraints, including box, group, and risk budget constraints. We'll formulate and visualize portfolios with different tail risk objectives. This includes equal weighted portfolios, minimum risk portfolio with a target return, tangency portfolio, and global minimum risk portfolio. Next, we'll construct efficient frontier in an interactive and customized manner and visualize it. We'll also initiate a short portfolio object and identify portfolios with different risk return objectives. Lastly, we'll also understand how to set up a portfolio in mean CVAR, that is conditional value at risk framework. In this video, we'll recap our discussion on mean variance framework. Recall the discussion with video topic on portfolio optimization. We started with 4 securities A, B, C, and D, and we kept forming different combinations of these securities A, B, C, and D. And as we keep on doing that in a return and standard deviation space, we obtain what is called feasible region. This blue region is the feasible region, which represents all possible combinations of return and risk, that is standard deviation. This feasible region is represented by this Eckert kind of shape, and each point here represents a combination of risk and return that is available to investors in the form of portfolios. Now, how do we improve our position in this feasible region? We can either go up or we can move left. And as we keep on doing that, we reach a particular surface or the surface of this Eckert region. This surface of Eckert region, this surface is called efficient frontier because every point on this surface represents a unique combination of risk and return, which can be explained in the following terms. For example, let's take this point Z. Now, for a given amount of return, this Z would obtain minimum risk, or for a given amount of risk, this Z would give you highest return. In a sense, every point on this surface obtains or achieves a very important, or we can call best combination of risk and return. That is, no other portfolio for a given amount of risk can offer you higher return, or for a given amount of return can offer you a lower risk, and therefore this is called efficient frontier given this property of portfolios lying on this surface. While we cannot directly compare these portfolios on this surface per se, individual investors, depending upon their degree of risk tolerance or risk averse nature, they will choose a given particular point on this surface. For example, an investor who is slightly willing to take more risk would probably prefer a position here, and therefore he would also be rewarded by a higher level of return. However, in contrast, an investor who is not so risk taking, probably more risk averse, and would like to take a position here, and therefore would be rewarded with this amount of expected return. In this backdrop, 2 points are very important, which is one is this S and one is this S dash. Because this point S offers the lowest amount of risk. This is the lowest amount of risk available across the entire feasible region. So any portfolio in this feasible region does not have lower risk as compared to S. So this point S is also called global minimum variance portfolio because it offers you the lowest variance across all the available feasible portfolios. Please notice this term feasible portfolio. Feasible portfolios are all the portfolio set that are possible within this feasible region. Another portfolio S dash is important because it offers you the highest return across the feasible region. So any portfolio, if you take any portfolio in this feasible region, S dash offers you the highest return. And the surface, this efficient frontier represented by SS dash, is a unique and best combination of risk return profile in the feasible region, and that is why we also call this efficient frontier, this SS dash region. Also, while discussing this portfolio optimization scheme and efficient frontier, we noted that if risk-free lending and borrowing rates are available, which are same, then one can also draw a tangent from RF to this efficient frontier. And this tangent line will touch, let's say, at point S. Then this S portfolio becomes one of the best optimum portfolio, and a new set of efficient portfolios will emerge, which comprise the line joining RF to S. We also noted that on the left of this RF segment, RF to S, this is called lending segment because any point on this portfolio which represents a combination of available risk and return, which is RF joining S, RF to S, can be obtained by mixing some amount of wealth in RF and remaining amount of wealth in S. Let's say if you are investing 40% in RF and remaining 60% in S, then you can obtain this portfolio segment which is called lending. We also noted that on the right of point S, there is a borrowing segment which one can obtain by borrowing at RF, because we said RF is available for both borrowing and lending, and therefore a slightly more risk-taking investor who is less risk-averse can borrow at RF and invest his own wealth at RS at this S portfolio, or the most optimum tangency portfolio, what we call, and remaining borrowed amount as well into S to obtain a position on this borrowing segment. And that is how this new efficient frontier is arrived. Importantly, this is also called two portfolio theorem or separation theorem, because now we need to only identify two portfolios, that is RF and the tangency portfolio S, to offer a wide range of risk return profiles, or what we call the new efficient frontier represented by this straight line. Also, now irrespective of investors or our clients risk profile, whether they are slightly more risk taking, less risk averse or more risk averse, we only need these two portfolios RF and S to offer them a combination or a choice or a portfolio of their taste and preferences that is desirable to them. So we have separated the decision of this portfolio RF and S from the investor's risk preference. That is why it is also called separation theorem or two fund theorem. To summarize, we recap our discussion on efficient frontier and mean variance framework. We also noted that mean variance framework employs variance or standard deviation as a risk measure. However, there are two very important risk measures that we also employ. One is called value at risk and another is called conditional VAR or conditional value at risk, or often referred to as expected shortfall measure, that we are going to discuss in the next two videos. In this video, we'll discuss a very important measure of tail risk, that is value at risk based models. If you are asked on any given day what is the probability that you can lose more than $10 million, then as a first step you'll try to plot your returns from negative returns to positive returns. These are your losses or these are your gains. And then also on the vertical axis you have frequency or probability density of returns. Often it is said that this kind of graph can be very nicely represented by normal or standard normal distribution. If you are using standard normal distribution, then on x-axis you have what we call z values or units in terms of standard deviations. This is a very effective way of representing the probability density distribution of variable like return. Let's say you plot this kind of graph and you find that at 5% cutoff, you start from this end to this end, and you find that 5% area stops or cuts off at a value of 10 million loss. Here, this point represents $10 million loss and the area under the curve is 5%. So 5% probability lies with a minimum value of 10 million. Then you say that assuming this was a daily distribution, then you can say on any given day, your loss can be more than 10 million has a probability of 5%. Either it can be presented in terms of absolute value or also in terms of return form, that is X percentage, talking about negative returns or losses. So there are two ways to express this phenomena. One, you can either say that there is a 95% probability that your maximum loss is $10 million, or there is extreme 5% possibility, there is extreme 5% possibility that your loss can be more than $10 million. So these are two ways to express the same thing. And in that case, it is said that your 5% daily VAR is $10 million. There can be a parallel negative return in the form like X% or losses that can also be expressed in VAR form. So let's say this 10 million VAR was X%, then you would have said that your 5% daily VAR is X%, which is negative losses or negative returns. Before I elaborate this formula in detail, please note that there are three important inputs to specify VAR. First, there is a time period. In the previous case, we noted daily period. It may be weekly or monthly as well. Second, the level of confidence, that is 95% or 99%. In that case, if confidence is 95%, then that alpha value, in the previous case, it was 5%. And if you take a confidence level of 99, then by the same logic, your tail probability that you are examining will be 1%. That is 1 minus alpha will be 99%, then alpha will be 1%. And lastly, the estimate of loss in absolute terms, this estimate of loss, this which was $10 million in absolute term or in percentages term. Now, from our knowledge of standard normal distribution tables, we already know that if this point is supposed to be 5% tail, the 5% probability, then this line is 1.645 standard deviation on the left. We can identify this point as 1.645 Z value. So Z value equal to 1.645 on the left side will correspond to that 95% region. That means area on the left side is 5% and on the right side is 95%. Now let's come to this formula. What does this formula mean? This formula is quite simple. It indicates the VAR value for a given distribution of returns. Let's say you want to have this alpha value or value of significance as 5%. Then the VAR value is defined as if we plot the return distribution for that given frequency, which is daily or weekly, the 5 percentile or 5% quantile, or you can say 5 percentile region, the minimum value in this region is the VAR value. Now, if you have plotted the probability density of return distribution, let's say, and you have identified this 5% probability region, the minimum percentile value will of course be that particular quantile or percentile. For example, we are talking about 5 percentile. That means the minimum value will correspond to exactly this 5 percentile cutoff point. This is what is represented by this formula, that the minimum value for a given chosen value of alpha percentile or quantile, let's say you're talking about 5 percentile, then the cutoff value is the minimum value of Z that corresponds to this cutoff. So which is nothing but simply the percentile value corresponding to the 5 percentile or alpha level. Now there are two ways to estimate this number. First is if you know the probability distribution. For example, if you believe that your variable or return follows normal distribution and you can plot them around in the form of normal or standard normal distribution, then in that case you can simply integrate over this region. For example, if I want 10% VAR, daily VAR, 10% daily VAR, then I can find a cutoff point on the left of which the area, because we are talking about probability density curve, then we can say the area under the curve is 10% of the overall area. And in that case, that integrated number, because we want area under the curve, that integrated part will represent the area, the cumulative area, the corresponding cutoff point Z corresponding to this 10% area will become my VAR value. So I can identify this Z value here, and this Z is nothing but returns in standardized form. So corresponding to each Z value, there is a particular return value which would be negative because this is the loss region on the left of 0. So we can identify that loss return, and that will be our daily VAR with that particular 90% confidence or 10% significance, or we can say 10% VAR, daily VAR is this value. It can be daily, weekly, monthly, depending upon the distribution of returns that is being examined. The second and empirical way is to have return data, distribution data, we can order this and start examining from the negative side, negative return, or the lower side. And let's say if you are looking for 5% VAR, then you can cut off the extreme extreme lowest 5% observations. You can cut off, let's say you have set of observations, you can put a cutoff line, and on the left of this cutoff line you have 5% observations. Then the cutoff point, the maximum return in this cutoff point becomes your VAR. In terms of magnitude, this will be the lowest value on the negative side, but in terms of signed value, it will be the maximum. And this will become our VAR. For example, let's say your values on the negative side are minus 5%, minus 4%, minus 3%, minus 2%, and minus 1%. Now, please note, in terms of magnitude, this 1% is the lowest. However, in terms of signed value, this is the highest, and this value, once we cut off at this level and we have these 5 values left, then this minus 1%, which is the highest, or in terms of magnitude, the lowest value, will become my VAR value. So we need to order our return observations and take the one which is highest in terms of magnitude, or lowest in terms of magnitude, and highest in terms of signed value. Mostly chances are it will be negative. So generally returns are symmetrically, to some extent they are symmetrically distributed. So you have negative as well as positive returns. So if you are ordering them from the lowest side, chances are that on extreme 5% or 10% you will have negative returns like this. This value at risk measure is very often employed by banks to estimate the performance of their portfolios and possibility of extreme loss events. To summarize, in this video we discussed the concept of value at risk and how it is helpful in estimating the tail risk of a security or a portfolio. However, we noted that there can be instances that can and obviously will go beyond, and extreme loss events that are beyond this VAR level, and therefore we need a slightly more accurate and efficient measure to handle those situations that are extreme situations and goes beyond this value at risk measure. In the next video, we'll discuss that one such measure, which is called conditional VAR or CVAR, or expected loss. In this video, we'll introduce a very important measure of tail risk, that is conditional VAR, CVAR, or expected shortfall measure. VAR method, value at risk method, that we discussed in the previous video, considers all the possibilities with a given certain confidence interval. For example, we said we are 95% confident or 99% confident. However, there are scenarios when this position is exposed to those losses that are beyond these levels of 95 or 99% confidence. And in order to cover this exposure that may happen in those extreme events, a more advanced version of risk measure, that is conditional VAR or CVAR, often referred to as expected shortfall, is proposed. The measure computes those losses, expected losses, given that this confidence level of 95% is reached. For example, given that you are in this extreme region, given that you are in this region, what is your expectation of losses? Let's say this is 99%, or if you believe 95%, then this region, if it is 95% cutoff, then what is your expected loss if you are in this region or this confidence level is breached? In order to answer this question, that we are talking about extreme event case, what is the expected value of loss? To answer this question, what we do here is we plot our returns on the opposite side. In contrast to our earlier plot where we had negative returns here and positive here, we essentially plot the losses, that means negative returns. So this will be our positive side, and these extreme scenarios will represent those extreme negative returns or losses. Now, objective here is to compute the expected or average or mean value of losses given that these events were to happen or occur. Let's take a simple case. Let's say you have 3 possible scenarios. Given that this scenario is breached, that is conditional sort of base probability that this extreme limit, alpha, it can be 5%, that means 95% confidence level, or 99% confidence level is alpha is 1%. This level is breached and we are talking about this region. Condition on that a priori probability is given that this region is breached. You have 3 possible scenarios. P1 probability, let's say 10%, that loss is 5 million. Let's say I'm putting negative sign for loss, and another 10% probability that loss may be 10 million, and 80% probability that loss may be 1 million. Then my expected loss, given that these are the only three possibilities, given that my losses exceed this level, then P1 into this minus 5, P2 that is 10% into 10 and 80% into 1 will be my resulting number. This is my 0.8, then this is 10 million, so 1, and then 10% with 5, so 0.5. So overall my losses are 2.1 plus 1, 0.5 plus 0.8, that is 2.3 million losses. So these are my 2.3 million losses, given that the losses exceed this level. So this is why this is conditional VAR, because condition that this VAR level is breached. So condition to that, what are my expectation of losses? Now this was a rather simple case for discrete events, and therefore it can be represented very simply like this, that condition, this is the conditional operator, condition that x is greater than var, that means my var level is breached, that is my given condition. What is the expected value of x, and which we simply computed as p1 x1 plus p2 x2 and so on. If your returns are in continuous form, or you believe that returns follow some kind of continuous distribution, then also the case is not too difficult. You have continuous value of return observations, you can plot them, and for each return observation there is a small probability density value that this return observation will materialize, or if you're talking about in terms of loss, then x value along with their probability density. And then you can integrate, this is 1 minus alpha region, please remember this is 1 minus alpha region, which is your critical region, your confidence level. Let's say here, if you're talking about confidence, let's say alpha we are denoting slightly in a different way. Let's say my alpha is my confidence of 95%. So if this region is 95%, this remaining tail region of 5%, which is 1 minus 0.95, this 5% region, I will integrate from this 1 minus alpha point to 1. So I'll integrate from 1 minus alpha to 1. I'll integrate this x value, and df is my probability density, which will also a function of x. So I'll integrate x df, where f is a function of x, starting from this 1 minus alpha point, assuming that this alpha was my confidence interval. So from this 1 minus alpha to 1, if I integrate, I'll essentially get this probability, which is my expected value of loss, given that the value has exceeded this var level, and it will be something like 1 minus alpha to 1 integrate x dfx. To summarize this video, we noted that CVAR method accounts for extreme scenarios that are not captured by VAR levels. For continuous distributions, the area under the tail segment, as we noted, which is essentially the loss segment, which was obtained through integration, is a very accurate measure of that expected shortfall or conditional CVAR measure. For discrete observations also, we noted that P1 x1 plus P2 x2 kind of probability weighted expectations can be employed to compute CVAR. Given that the VAR levels has exceeded, the a priori probabilities of these extreme losses P1, P2, P3 and so on can be multiplied by these extreme loss events x1, x2, x3, and these probability weighted expectations are used to compute our conditional VAR. As we start our journey of portfolio construction and its implementation with R programming, in this video we'll begin with downloading data from a very powerful and publicly available data source, that is Yahoo Finance. We'll start with downloading the securities. First, we'll download the relevant packages, starting from library command f portfolio, that is the most important package for this. Then we have library tidyverse, and we'll keep these packages loaded for times to come, so that whenever we are running a function related to portfolio construction or portfolio optimization, we are able to run those. Another important package, the library zoo. We have library quant mode. Now that we have loaded the relevant packages, we'll start with the downloading securities. As a sample, let me show you. If I download a single security, I need to know, and please remember, I need to know the ticker on Yahoo Finance in order to download the security. I already know that Amazon has a ticker AMZN. So I'll use this get symbols command. I'll use this get symbols command and this symbols. I need to provide the symbol that I want to download, which is Amazon. Now here I am downloading a single security. I am downloading all the data in this AMZN object, and I'll put this command auto.assign. I'll put this command auto.assign equal to F, and I'll supply the period also from maybe 2010 1st of Jan. So this is my starting period, and I'll provide this data to 2021 December 31st. So this is my closing period. Now when I run this command, notice when I run this command, Amazon object is created on my environment. So when I run this command, notice as this command is run, data from Yahoo Finance is loaded. Let me see. Let us examine this object. So we have the following data, which is open, high, low, close, volume, and adjusted price is loaded. So we'll use this adjusted price series, which include any adjustment for dividend and other cash flows. So we'll use this Amazon.adjusted pricing. Let us examine the class of this object. So this is XTS or Zoo kind of object that is downloaded. Now please remember, in order to construct portfolio, we need to download multiple objects. So for that, again, similar code is used. Let's call this multiple series object as DF or data frame. I'll use the same command with same symbols, get symbol. This get symbols command I'll use. But this time around, I'll provide a number of symbols because we need multiple stocks to construct our portfolio. So first, this symbol, this is for Nifty 50, NSCI, this is for Nifty 50. And I'll provide it in vector form. Next, we have this JSPC. This is for S&P 500. Later, I'll specify their more accurate names to avoid any confusion. Then we have FCHI, which is for CAC 40, major index in France. It's a major national index. Then you have GDAXI. This is for DAX Germany, major market index in Germany. Then you have FTSE. This is for FTSE 100 in UK. Next you have stocks, which is major Euro stocks index. And then you have Russell, which is another Russell 2000, which is another major index. For this, which we have RUT. So these are the major indices that we have signed. Now, interestingly, in this particular command where I'm loading multiple securities, I'll not use auto.assign as false. I'll set auto.assign as true. So all the symbols will be separately loaded in separate objects, not assigned to this DF. And I'll use the same time window. The time window I'll keep as same, which I used earlier. And now I'll load this. Notice when I run this command, in my data environment, all the objects are loaded separately, and each object contains the data. And now I need to combine the entire data object. So I need to use the tickers by the name they are loaded. Ticker, let's call them tickers. And I'll use these tickers as list objects, combine them. First is NSCI, Then I have JSPC. These names are the names by which they are loaded in my environment. I'll change them to more suitable names shortly. GDEX, FTSE. So these are my objects. I'm using major market in D6. These are generally less noisy, so portfolio construction is expected to be smooth without any hassles of thin trading, issues related to thin trading and so on. So now I'll run this command and load and create a this object tickers, which is a list object. I'll merge, and this ticker, if I print this ticker object, notice it carries the consolidated thing. From this consolidated thing, I'll merge. These are all in the list form. So each object is contained individually. So I'll bind them together. Let's create a new data frame df1, which will essentially bind all the objects. Let's use this merge command to bind them. It will bind all the objects. Once I have bind it in df1, notice a large extensible time series XTS object. I'll select only adjusted prices. And how do I select only adjusted prices? It's quite simple. I'll use this final let's call it final underscore df, where I'll filter the df underscore 1 series, which is my combined consolidated series. I'll use this string detect command, and in this string detect function, I'll supply the column names of this df1 object, and I compare it with the term adjusted. Those columns or variables where this adjusted term is there, they will be selected and remaining will be ignored. And if I have done it correctly, let me look at final dot underscore df object, and let's see what kind of columns are there. Notice all the indices, only their adjusted prices, the column with the adjusted prices are appropriately selected. So this is my final data. To summarize this video, we loaded the relevant packages of F Portfolio, Tidyverse, Zoo and QuantMode. Then we demonstrated how to download data for Yahoo Finance using a single security, that is Amazon. After that, we downloaded a number of securities from Yahoo Finance, that is Nifty 50, S&P 500, CAC 40 from Paris, DAX Germany, FTSE 100 from UK, stocks from Euro, and Russell 2000. And then we combined them, extracted their adjusted prices in our consolidated data frame format, which is final underscore df. And this will be further used in the subsequent processing and return computation. In the next video, we'll compute the returns and we'll try to visualize the data. Now that we have downloaded the data, let us start by properly naming it, naming the variables or the security prices, and then computing returns and subsequently visualizing it. So as a first step, we will give appropriate names to the column. So we'll name, compute returns, and visualize. So as a first step, let me just give the names with this call names command. Here I'll use final underscore df. This was our original data that we downloaded, but we give it appropriate names. The first name is Nifty. So since we downloaded Nifty 50 data, I'm giving it a name Nifty. Then S&P 500. So let me put it as SP, or more appropriately S&P. Next column is CAC. Then DAX. Then FTSE. Next we have stocks, Euro stocks for stocks. Then Russell 2000. Let me call it RUT, that is Russell 2000. So this is my final variable. Let me name these. And if you want to check whether names have been appropriately given, you can again type final underscore df, and you'll find that if I enlarge my console window, you can notice the names that I have given are here visible. As a next step, let me compute the returns, and a very simple and interesting command. Let me call the new data as final underscore df underscore ret. So this command will compute returns, and it's very simple. Diff log. This is a very simple command. It takes the first difference of the series in the log form, which is essentially log returns. This is very easy to do, those of us who have computed return in the past. So those of us who have computed returns in the past, they will know that this command will first create the log of the price series and then take the difference, which is sort of returns in the continuous form. And now that we have this return variable available with us, let's see the head of this final underscore diff object that we have created. Let's see the head of this object. Yes, the returns are computed. The first object is obviously NA because we use the first price series. There's no previous price, so the first prices are NA. We can, in fact, to avoid any kind of trouble, we can just type this command and we'll use this na.omit to remove NAs from this object. So I'll remove the NAs from this object. Now NAs are removed. Also, this F portfolio object or library that we installed, it generally works well with the time series objects. There's a certain time series format that it's more suitable. So we'll run this time series command. And with this time series command, we'll convert our final dfret object to essentially to this final return object. So let me name it as final ret in fact. So this is my final return object that I'll be using. So now that we have downloaded and combined our data into final return form, let us start with a little bit visualization of the data. So we'll visualize the data now. To summarize, in this video, we gave the names to variables. So we appropriately named the variables with their proper security names, and then using diff log command, we computed the returns, and then we removed NA observations, and then we converted our return object to a more suitable time series object. In the next video, we'll try to visualize data and see its properties. In this video, we'll try to visualize the data. So we'll try to visualize the data. Let us start with a simple visualization command, which is plot.xts, and we'll supply this function plot.xts our final data frame, which is final underscore df. This data contains prices. We'll supply, since we have 7 price series, 7 indices, we'll use 7 colors. So this command will ensure that there are 7 colors, 1 to 7. Then central heading is all prices because we are using price series, and then we'll keep the y-axis as empty. So now I can run this command. Notice that once I run this command, I get all the price series on my chart. I can see all the prices. Also, you may want to plot all the series individually rather than putting them in single plot, so that you can make a more appropriate comparison and see their variation properly. So for that, you can slightly tweak the command. For example, you can type plot.zoo and then supply the same object final underscore df. You can again supply all the different colors since we want to plot all the prices in different colors. Again, we'll put the central heading as all price, but this time we'll specify that plot.type is to be plotted in multiple windows. So we'll specify this multiple argument so that plotting is done with multiple windows. Also, we'll keep the y-axis as empty, and then we can use this 6.main argument to increase the size of central heading. Probably a larger central heading will plot. Notice now all the prices are plotted with different colors and different plot windows. You can see their movement more clearly than on the single plot. They are all visible. You can zoom it also. You can zoom the prices and see it. Sometimes you may be not very sure that which window plots which color or which window plots which series. So you can remove this y-lab which was empty, and now if I run this command, now this command is run where I have not specified the y-axis, so the original name from the series will be picked up. Let me just enlarge the plotting window so that we can see the graph appropriately. So if I run this command, notice that now the name of the axis that I specified earlier is also provided. So for example, Nifty is the black one, S&P in the slightly reddish color, CAC is green, and so on. For example, Russell is in sort of brown yellowish color. So we have all the indices that we can identify individually, in fact, on all the 7 indices individually on the graphs. Let's try to plot returns now. We'll make use of same commands. It's quite easy. So now it would be more appropriate to plot the return diagrams, return graphs on separate windows, because return is very fluctuating around mean of 0. It generally it is very fluctuating, so it would be appropriate if we plot them on separate plots. So again, I'll use the plot.zoo, but I'll supply the final return argument. Here we have the returns, all the returns available. Again, all the 7 will be plotted in different colors. Central heading is all returns because this graph carries returns. We'll specify the plot type, plot.type as multiple, so that they are plotted in multiple windows. And I'll not specify the y-axis so that each plot has its own index or return name. I'll just specify that sex.main equal to 3 so that slightly larger graph is produced. So now let me enlarge the plot window before I run the command. So sufficiently I've enlarged it. Now once I run it, notice all the individual indices are plotted and we can see the fluctuations. In fact, we can see around 2000, around somewhere around after 2000, there's a large jump. We can see here this large jump, and this is common to all, and in between also the fluctuations happen because these are broad market wide indices. So whenever there's some kind of global crisis, there would be some kind of co-movement, high volatility and falling prices, which is what we are seeing here, and all the indices are plotted in different colors. Also, a slight modification in the command. If I remove this zoo, notice if I remove this zoo, now the dates are plotted. So I can, now I have all the individual indices and their dates are also available with me. So I can identify these fluctuations, their timings. You can see there, these timings are around somewhere around 2020. There's a sharp increase in volatility, particularly the down, which is also associated with falling negative returns. So we can say this is probably around COVID period, and it is common to all the indices. As a last step, when you are summarizing the data, you have already plotted it, you have visualized it. As a last step, it is always advised to create a summary measure. So just summarize your data by typing summary and supplying your final return object. So it's nice that it will give you the final summary thing. You can see that summary of all the returns is provided here, nicely printed summary. You have start and end date of the record, and you have Nifty, S&P, the summary returns are also provided. Nicely printed summary. We can see that extreme negative returns are always mostly dominating the returns. Mostly these series are negatively skewed as it appears. To summarize this video, we plotted the security prices together in a single graph. Then we also plotted them in separate graphs. Then we plotted the returns. We can see that returns are negatively skewed, especially during the COVID time. There was large fluctuation and negative returns. This we confirmed with the summary measure. We summarized the returns and saw their distribution: minimum, maximum, mean, median, first and third quantiles. We observed extremely negative returns are slightly dominating, so the return appear to be skewed. We'll conclude with the visualization in the next video, where we'll examine the density distribution of all the returns.